So guys, welcome. This video is for D and A block. So as the chapter is inorganic chemistry and there is uh, no new thing about it, about D and A block. Some important topics are there. I will discuss all of them. So I am making a video instead of a class. So actually those persons who have done your coordination chemistry well, you can also do the D and A block easily. So let us start the D and A block here. Okay. So what happens? D and A block. At first, we have to know which are D and F block elements. The in periodic table, group number 3 to group number 12 is generally not. It is known as no. Generally was correct. Generally is correct. Generally known as D block element. Actually, the D block elements are also called the transition elements. Okay, so they are known as the transition elements. Okay, and F block elements are known as the inner transition elements. So in our syllabus, the first series of transition elements are there, which is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So these are the first row transition series. Okay. So these are in our syllabus. So we should see some of the reactions and their properties. So at first, we'll see the properties of our D block elements. So I'll discuss all of them one by one. I'll give it slowly. Okay. Number one, they have variable oxidation state. Number two, they can be used as catalysts. Number three, they are generally colored. Number four, they have high values of atomization enthalpies, except zinc, cadmium Hg, all of them have very high melting point or boiling point. Okay. Okay. Again, number six, they have sorry the trend of ionization enthalpies are not as smooth as S block and P block elements. So these are some fundamental properties I am trying to discuss, and then we'll discuss it more and more details. Let us see. Okay. So at first they can show different oxidation states as what is the definition? At first, what is the definition of transition elements? The definition is lies that the definition is that the elements which has partially filled d orbitals are known as transition elements. The elements which has partially filled d orbitals are known as the transition elements. You can see here, such as scandium, you can see 4s2 3d1. This only you can remember this. You should remember this one. Scandium does not show variable valency or oxidation state. The oxidation number of plus 3 is the most stable. So scandium, you see 4s2 3d1. Titanium 4s2 3d2. Similarly, vanadium 4s2 3d3. You can see chromium 4s1 3d5. But you can see zinc, that is your 4s1 4s2 3d10. You can see cadmium 5s2 4d10. You can see mercury 6s2 5d10. So by the definition, what is the definition? The definition is the elements which have partially filled d orbitals, but these three have fulfilled d orbitals, so they do not belong to the transition series. Actually, they do not belong to the transition series. You should remember this one, but they are present here. You can see here, here zinc, cadmium, Hg have fulfilled d orbitals. So by the definition, they do not belong here. So, but they are present here. Due to the similarities of their properties with rest of the transition elements. So zinc, cadmium, mercury does not belong here. They are present here due to the charge balance. But my target is that we have to discuss all the properties. It is just an introduction. We are at first we'll see why they can show variable valency. You can see why they can show variable valency. You can see here, such as you can see in case of titanium, in case of manganese, iron, etc. I'm picking up random examples here. So titanium, manganese, iron, etc. You can see here. You can see yes, so chromium also you can see. Okay, now you can see titanium has 4s to 3d2. So you can eject one electron by slowly, one electron at a time. At first, when it is Ti plus 1, you can see this will become 4s1, 3d2. Ti plus 2, this will become 4h0, 3d2. Ti plus 3, that is 4h0, 3d1. Ti plus 4, 4h0, 3d0. This one is the most stable form actually, because both of the valence orbital are empty. So three types of stabilities are there: half filled, fulfilled, empty. So this is empty in nature. That's why the Ti in plus 4 is stable, and you can see a max number of compound: TiCl4, titanium tetrachloride, TiO2, titanium dioxide, used in medicinal use, coloring agents. It is also used to make amber glass, etc. You can see different kinds of reagents which are used: TiOCH3 whole 4. These are the evidence that your titanium is stable in its plus 4 oxidation states, not in other oxidation states. Similarly, you can see in case of manganese, you can see the electronic configuration of manganese. Electronic atomic number is 25, so that is 4s2, 3d5. It's 4s2, 3d5. So it can also show a variable oxidation number. Manganese plus 1, that is equal to 4s1, 3d5. What happens actually? I'm writing here. In case of 4s and 3d, the the first electron is released from 4s because it has a lower amount of energy. Actually, both of the orbitals have near about similar energy. And always remember, your Aufbau principle theory is only valid for empty orbitals. Yes. Okay. So we are discussing another thing. This is the point we should note down here. Actually, this is more important. So let us see. Again. Manganese, the electronic configuration is 4s2, 3d5. Now what happens? You can see here manganese. It is manganese plus 1. It equals to 4s1, 3d5. You can see again manganese plus 2. This is 4h0, 3d5. Manganese plus 3. This equals to 4h0, 3d4. You can see the third ionization enthalpy of manganese is very high because the configuration D5 configuration is highly stable. You can see here, and you can see manganese plus 4, 4h0, 3d3. Manganese plus 5, 4h0, 3d2. Manganese plus 6, 4h0, 3d1. Manganese plus 7, 4h0, 3d0. You can see that plus 2 is a stable oxidation state. +7 is a stable oxidation state, because these are the electronic configurations are those in which you can see that the orbitals are in the stable configuration. That's why these kind of oxidation numbers, it can show variable oxidation numbers, but this is not necessary that in all kinds of oxidation states it will be stable in nature. Okay, the stability depends upon the electronic configuration. Okay, so again, you can see in case of iron, it is also possible here. In case of iron, you can see 4s2 3d6, iron in +2. You can see 4s0 3d6, iron in +3. It will produce 4h0 3d5. So +3 is more stable. You can see d5 configuration is there. That's why iron gets rusted to produce Fe2O3 whenever it is present in the contact of oxygen in presence of your water vapors. So you can see they can show variable oxidation number, but this is not necessary that they will be stable in all kinds of oxidation numbers. You should see the second and third transition rows or transition series elements can show higher oxidation numbers, such as you can see osmium and ruthenium. They can show +8 of your oxidation number. Also, higher valencies, okay, such as you can see here, OSO4, osmium tetroxide, okay, ruthenium tetroxide, ReO4. Again, you can see some of the examples, such as your ruthenium, rhodium, etc., Rh. They also can show different kinds of higher oxidation numbers. You can see here this is the Wilkinson's catalyst. Again, you can see Ru PPH3 whole 3, okay, Cl hydrogen. This is known as this is not a Wilkinson catalyst, but the action is like the Wilkinson catalyst. Okay, so you can see they can show higher oxidation compounds, oxidation numbers, or higher amount of valencies. Iridium can compound Vasca's compound, which is also show higher oxidation number. It is the orange yellow in nature. So there are such as you can ruthenium can form ruthenium red. Ruthenium can form ruthenium red. Okay, they can form a higher variable. They can form huge amount of compounds which have high oxidation numbers and high valencies. So it is not necessary that all of them should show similar oxidation numbers. The oxidation numbers may be different and vary from transition series to series. In the second and third row series, they will show a higher oxidation number, and they will be stable in also higher valencies and higher oxidation numbers, such as you can see here. You can see here there is a great example here. OSO4 and your KMNO4, both of them, it is in the +8 oxidation number, it is in the +7 oxidation number, but this converts into +6, this converts into +2. You can see the stability of their oxidation numbers is not same at all. The third and second row, transition elements want to show higher oxidation number. That's why you can see here. That's why, that's why, that's why you can see here that KMNO4 is a strong oxidizing agent. KMNO4 is a strong oxidizing agent. You can see here. You can see the change in oxidation number is 5 unit. The change in oxidation number is 2 unit. So you can see that. So KMNO4 is more it's wanting to or more or is more prone to undergo the reduction to your plus 2 oxidation state as as it is stable in plus 2. Okay, it is stable in plus 2. But in case of osmium, it is stable in plus 6. Okay, that's why the change in plus 8 to plus 6 is very low, but the change in plus 7 to plus 2 is very high. That's why this kind of phenomenon or appears. Okay. Again, the first point is over. They have the first point is over. They can show variable oxidation number. Second point that is the second point, that is they have high values of atomization energies. Why? There is also a very good reason here. You should know the reason and remember the reason. Remember, it's actually very easy. The energy of atomization of the transition elements such as tungsten, chromium, you can see your tungsten, chromium, etc. are very high, but zinc, cadmium, Hg are very low. Why? Actually, higher the number of unpaired electron, higher is the amount of metal-metal bonding, higher the bonding, higher is the amount of energy required to break the bonding. To break the bonding. So higher will be the atomization energy. But there is a problem here. Manganese abnormally show. You can see here. You can see here. In case of manganese, you can see there are D5 configuration. D5 means you can see here 5 unpaired electrons are present. 1, 2, 3, 4, 5. 5 unpaired electrons are present. So higher number of multiple bond, higher number of metal-metal bond should be present, but it shows abnormality and has a low melting point. Okay. But in case of you can see your zinc cadmium energy, in case of your zinc cadmium energy, in case zinc cadmium and Hg, you can see here zinc has a 4s2 3d10 configuration, cadmium has 4s2 5s2 4d10 configuration. Mercury has 6s2 5d10 configuration. So it is evident from here that there is no unpaired electron. So no metal metal bonding or a weak, you can see here, weak metal metal bonding. That's why they have low melting point. That's why they have low melting point and low atomization energy. So we should remember that higher the number of unpaired electrons present, generally higher will be the metal metal bonding, and that's why uh, higher will be the difficulty to make the molecule into atom, and the enthalpies of atomization is so high that they have shows a very high melting point also. So some of them shows some of your bad properties or abnormal properties, such as your technetium and your manganese. They will show the abnormality, and they will, instead of uh, though they have not instead of though they have high number of unpaired electrons present in them, but they will show a low melting point comparing to the rest of the elements present in that series or in that group also. Thank you. Uske baad, next one. So this is the enthalpy of atomization. The next point is color. Because you know that every kind of color comes from your electronic transition. What happens? This is very easy actually. So electrons are present here. We have discussed in atomic structure, chemical bonding, and also in your coordination compounds. You can see here electrons are present in the ground state. But when you give heat here, or it can absorb the energy from the environment, it gets excited here. Now what happens? As they have gone to the higher state or higher excited state, they are not stable there. They will come to its original position by releasing the energy in the form of an electromagnetic spectrum. The color that was absorbed, the complementary color will be seen according to the theory. But the transition elements are intensely colored. Okay, they are intensely colored. Okay, you can see the chromium uh, in different kinds of oxidation states. You can see that it's in dichromate. In +6 it is orange in nature, and it is in case of your +3 chromium sulfate. In case of +3 chromium sulfate, chromium chloride, etc., it will show chromium hydroxide, etc., CrOH3 will show a very classical green color. Okay, again you are in chromate. Okay, CrO4. Okay, CrO4 2 minus. I'm writing the question. Cr in +6 is a orange yellow, or yellowish red. You can say orange red. You can say orange red. In case of +3, it is green in nature. Green in nature. You can see it's very easy. Green. Cr in plus. I think CrO4 2 minus. Okay, CrO4 CrO4 2 minus. Okay, CrO4 2 minus means +6. Barium chromate. Barium chromate here. It is also can show plus +6. It can also show yellowish color. Actually, it's yellowish or UYE yellowish, orange, or red. Yellowish. Okay, so you can see they are intensely colored. You can see manganese in +7 is very intensely colored. In case of KMnO4, it is purple in nature, intense purple in nature. Ruthenium, it can produce ruthenium red. Okay, platinum can form the Mughal blue or royal blue. Okay, iridium, Bhaskara's compound, it can also produce your orange red. or very fine, shiny, orange color. Okay, so these properties actually depends upon their electronic transition. What happens? What happens? This is known as the DD transition. DD transition. What happens? What is the DD transition? As the energy gap from a lower D to upper D orbital is so high, when the electrons go to that upper D orbitals, they take high amount of energy, but when returning back to its original position, it releases that high amount of energy, and colors are seen. Though the intensity depends upon various factors or Lambert BR law, so here n by n0 is the occupation of the electrons in the higher state, n0 is the ground state, g is the length splitting factor, e is the exponential term, epsilon is the constant, c is the concentration, as the length of the solution through which the light has been passed through is the DD transition. Actually, 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 all the elements do not undergo DD transition. The most important point is that if there is a center of symmetry in the, if there is center of symmetry in the compound, then there is no DD transition, such as you can see in some complexes, such as this should not see, this should not show any color, but it shows weakly colored. It is weakly colored due to the disruption of the center of symmetry by your asymmetrical stretching. Asymmetrical stretching. I'm explaining you that. You can see that the axial CN bonds, axial bonds which are present with iron, the cyanides will vibrate continuously, and uh, at first you can see there is a center of symmetry in the molecule. Okay, the molecule is purely symmetrical in nature, but whenever the vibration of the axial bonds occur, the 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 problem is that the center of symmetry gets disrupted. When the center of symmetry gets disrupted, and the electronic transition or the DD transition may occur, but for a very short amount of time. Actually, the molecules which does not contain any kind of symmetry, any kind of your symmetry, that's why center of symmetry. So that there is a no symmetry, that means there is a good electronic transition is present and DD transition is there. But in case of this kind of compounds, which generally contains that generally contains your center of symmetry, but what happens due to some amount of some any kind of phenomenon or any kind of asymmetrical stretching, the center of symmetry gets disrupted there, and the electronic transition may occur in that kind of compounds. So you can see that they, but that is for a very short amount of time. Electronic transition takes only for 10 to the power minus 14 seconds. Okay, so the center of symmetry will be disturbed for a very short amount of time, and that time the electronic transition occurs, and the intensity is very low because electron does not get the time to get to the higher d orbitals. That's why they will show a feebly colored or weak color or weak, or they will be feebly colored in nature or weakly colored in nature. So these are the very good important examples of DD transitions. But what happens? You can see here there is a very good example here. You can see in KMNO4 permanganate, the rigid structure is present. As it is rigid in shape, so no transition, no DD transition occurs. You can see tetrahedral molecules, tetrahedral molecules never have a center of symmetry. So there is a DD transition. There is a DD transition which that's why they are colored intensely. Okay. Okay, you can see no DD transition, but KMNO4 is very intensely colored, but KMNO4 is intensely colored due to the charge transfer from ligand to metal. Because you can see here, in case of KMNO4, it is in the +7 oxidation state. That means it is electron poor. And this is in the -2 oxidation state. That means it has electron rich. So ligand to metal charge transfer occurs. Okay, that's why the color is intense, though there is no DD transition. This kind of example you can see RuBiPy whole to ruthenium bipyridyl. This is also a charge transfer complex. So you can see that the transition elements are colored intensely as due to the DD transition or charge transfer. It is not necessary that the charge is transferred always from the ligand to the metal. It can be the reverse also. The charge can also be transferred from the metal to the ligand. Okay, so this kind of phenomenon also occurs from the metal to ligand. The metal is electron rich, then the ligand is electron poor, then the charge transfer can occur from the metal to the ligand. This is possible. Okay, thank you. Next one. The size of the atoms goes on decreasing while going from left to right, because due to the increase in the Z effective. As the number of electrons increases in the orbital, its screening power decreases and the Z effective increases. So the size decreases. This is called the transition contraction. Okay. This kind of phenomenon is also known, seen in your lanthanoids also. I am just covering the topic here, lanthanoid contraction also, because it is very important to you. Here, I will give you some examples also. Lanthanoid, lanthanoid, if the spelling is wrong, if you know that, you should correct it, okay? Lanthanoid contraction, okay? Or it's also called lanthanide contraction. What happens? I am first telling the phenomenon here. You can see in your lanthanide series, you can see they are known as, in Bengali, they are known as Birol Mrittika Molo. Birol Mrittika Molo means they are not found in enough quantity in the earth crust. Generally, they are found in a very low concentration. Lanthanoid contraction is a special kind of phenomenon here. You can see actually what happens in the transition series. They are D block elements. So D block elements means last electron enters the D block or D orbital. D has a higher screening power than F. The actual phenomenon is S has a most screening power, then P, then D, then your F. You can see here. So F is the most pore screener. So what happens? You can see what happens. You can see that F is the most pore screener. In case of d orbitals, okay, you can see while an electron goes into a valence shell, such as an example, you can see scandium. Okay, scandium, you can see scandium, it has a 4s2 3d1. In case of titanium, 4s2 3d2. What happens? This electron here and this electron here, as the atomic number increases, number of electrons in the valence shell also increases, because you're seeing that here. So as the number of electrons are increasing, as the number of electrons are increasing in the valence shell, you should remember the screening power of the orbital goes on decreasing due to the interelectronic repulsion shift. What happens? When the electrons are entering into the valence shell, it is getting heavy and heavier. The orbital is getting heavy and heavier. So as it is becoming heavier in nature, and you will see that number of electrons are increasing, so there will be a interelectronic repulsion. As the interelectronic repulsion is increased, you will see that the screening power will decrease. So what happens? As the screening power decreases, the Z effective increases. So the nucleus will attract the electron towards itself in a tighter way, or in a high attraction power. So the size of the atom will be lower. What happens? Actually, what happens in case of F? The effect is prominent. The effect is very, very prominent. In case of D, the effect is not so much prominent. It is prominent. You can see that. But the size difference in size from one F block element to another F block element, or one lanthanide to another lanthanide, series element, you will see that the size difference is large. But in case of D series or transition series, or it is called the transition series, you can see the size difference is low. Why this happens? Because F is the most poor screener. Most poor screener. What happens? As the electrons in the F orbital increases, as the electrons in the F orbital increases, what happens? The screening power of the F becomes so and so less, that the Z effective increases highly or in a higher extent. That's why the electrons are slightly or very tightly held or attracted by the nucleus, and the size will become very low. So I'm giving you an example here. While you go from scandium to titanium, the difference in size is not so much as it is the size difference in case of lanthanum to cerium, because F is a poor screener. While the F becomes heavier, the screening power of the orbitals becoming very, very low. That's why the Z effective will increase. So this is known as the lanthanoid contraction, and this is a very important phenomenon. There are many of the phenomenons in the periodic table which will definitely depend upon your lanthanoid contraction. I am giving you some examples here. At first, I am giving you the definition. Lanthanoid contraction means while going from lanthanum to lutetium, lanthanum 57, lutetium I think 71. If I'm not wrong, I think lutetium is 71. While going from lanthanum to lutetium, there is a continuous decrease in the size due to the increased Z effective. As the increasing atomic number, the electrons are involved or added to the valence shell, that is the F orbital. You can see that while the electrons enter into the F orbitals, the orbital become heavy and heavier. That's why the size of the elements decreases in a greater extent. You can see in case of inner transition series, this is known as the lanthanide contraction. This kind of similar phenomenon you can also see in the 5F elements. They are called the actinide contraction. So there are three types of contraction: transition contraction, lanthanide contraction, and actinide contraction. The most prominent is the actinide contraction because 5F is a more poor screener than the 4F. So this is known as lanthanide contraction. So the phenomenon I'm telling you again here, there is a, while going from lanthanum to lutetium 57 to 71, you will see there is a continuous decrease in size, and the size is difference in size is very, very high. Okay. So what happens while going from left to right in the lanthanide series? You can see that the size decreases continuously because what happens while the electrons are added, as the atomic number increases, electrons are added in the your valence shell, that is the F shell. What happens while you increase the number of electrons in the F shell? What will happen? The interelectronic repulsion will go on increasing. As the interelectronic repulsion go on increasing, what will happen? The shielding power or the screening power will decrease. As the screening power decreases, the effective nuclear charge increases and the size will get decreased. The effect is prominent because F is the most poor screener. So I'm giving you some interesting facts here. You'll see that. You'll see that zirconium ZR and hafnium HF, they have, it's a very important question. Boards and entrances. Boards and entrances, here you can see that very, very important question. What happens here? You can see zirconium and hafnium has almost similar sizes. Almost means very, you can say same. You can say same because the size difference is very low, same, and they have same properties. As you can ask me, they are present in the they are present, as you can see me say me, they are present in the same group, so they will definitely show the same properties. No, sodium and potassium are present in the same group. Lithium is also present in the same group. They are similar in properties but not same. Not same in properties, not same in properties. Okay, they are similar in properties, similar and same is not same. Okay, similar properties, not same properties, but they will show the exact same property, the same amount of electronegativity. They both shows the HCP structures. Okay, they also show some defects there. Okay, so you can see that they both shows HCP structures, and you can see that they have same electronegativity, same specific gravity, same metallic character, same metallic radius, same amount of reactivity with the acids, same amount of electropositivity, or they have same amount of atomization energy, same ionization enthalpies. Why? Because you can see that while going from zirconium to hafnium, what happens? Generally, what happens? Generally, while you go from top to bottom, while you go from top to bottom, what will happen? The size will increase. What will happen? The size will increase. Now, what happens as hafnium? As hafnium is a post-lanthanoid series element, hafnium is a post-lanthanoid series element. I think the atomic number is 72. What happens? So the size should be increased from zirconium to hafnium. But what happens? As it is present, in the after the lanthanoid series, what happens? The effect of lanthanoid contraction. Falls on it. That means what? The increase in size, from zirconium to hafnium, will be cancelled out or will be quenched. This is a special English term. It's quenched or cancelled out by the decrease of size due to the effect of the lanthanoid contraction, as it is a post-lanthanoid element. Again, I am saying that while going from zirconium to hafnium, the size will increase, but due to the lanthanoid contraction, or due to the effect of lanthanoid contraction on the hafnium, the decrease in size also occur. So this is why zirconium and hafnium show similar properties, and they have not similar, same properties. Actually, their size is same, and they are also present in the same group. So they have same electronegativity, same metallic radius, same amount of reactivity, etc. Thank you. So this is the lanthanoid contraction. Okay. We are moving on here. The D block elements shows complex forming properties. What is complex forming property? There you can see that their charge density is high, and their d blocks or d orbitals are exposed. So the d orbitals can come in the influence of the ligands and can be splitted into two different d orbitals, as we have seen in our complexes, T2G and EG. Okay. Now what happens as they come in the influence of this one? Okay, they can form complexes. D orbital is much more exposed, but you can see this is, if we compare the complex forming tendency of D block and F block elements, F is much more diffused or buried into the atom, so does not come in the influence of the ligands. So doesn't come in the influence of the ligands. So do not show complex in tendency. Now we'll go to the ionization enthalpies. Okay. No, at first we'll see the ionization compounds. What happens is actually more important. Ionization energy. You can see if the electronic configuration are stable, then the ionization potential are also high. Why this happens? You can see here, such as you can see, you can also see the first row transition elements show +2 oxidation state as their general or characteristic oxidation state. So you can see, actually, it is important to IP1 also understand IP2 and IP3. Question comes in the exam that the IP3 of zinc is very high, that very high, or or question comes, why zinc, cadmium and Hg salts are colorless? You can see it is very simple. Zinc has an electronic configuration of 4s2 3d10. 4s2 3d10 means you can see two electrons will come from these two, 4s0. Now what happens? 3d10. In case of zinc plus 2, this is 3d10. What happens? It is most stable in nature because d10 configuration, exchange energy concept, most stable. That's why this will lose one electron to get unstable. That's why it will resist. It will resist the release of one electron from this d orbital. That's why. That's why it will never show. It will never show a +3 oxidation state. So what happens? Zinc, after losing two electrons, it will become more and more stable due to the d10 configuration, which is highly stable in nature due to the exchange energy. That's why what happens, it will not release any more electron because it will become unstable in nature. That's why it does not release energy electron. That's why zinc +3 is not possible. So +2 is stable in nature. And again, you can see here in +2 oxidation state, you can see the d orbitals are fulfilled in nature. So there is no unpaired electron. So as there is no unpaired electron, this will not undergo any kind of DD transition because unpaired electrons only can undergo the DD transition. Okay, that's why it is diamagnetic as well as colorless compound. Or you can see the most of the zinc salts are white in nature. Not it's white; it is actually colorless in nature. So zinc, cadmium, Ag, mercury salts are generally colorless due to the presence of completely filled d orbitals. That's why they will not show color in nature. Again, you can see the third IP of manganese also comes here question. Again, you can see manganese is 0 of Mn+3, Mn+2 and Cr+3. The Cr plus 2 is very high. So what happens? You can see that it is very difficult to convert it Mn plus 2 to Mn plus 3. Okay, because Mn plus 2, what happens? You can see in case of Mn plus 2, you can see that this is 4s2 3d5. Sorry, Mn neutral. Mn plus 2, you can see that it is 4s0 3d5. Okay. Now what happens? 3d5 is a stable electronic configuration. So stable electronic configuration. So it is very difficult to release or eject one electron from Mn plus 2 to make it Mn plus 3. But whereas in case of chromium, it has a 4s1 3d5 electronic configuration. In case of plus 2, it is 4s0 3d4, which is unstable in nature. That's why you can easily eject one electron. That's why Cr plus 2 to Cr plus 3 can easily be converted. So this is the answer. Actually, there are questions that come in our exam that why IP3 of manganese is very, very, very high. This is why, because after releasing two electrons, the manganese will get more and more stable due to the half field d orbitals. So this will you should remember here. So electronic configuration plays an important role in case of here. Though the E0 values not show a smooth trend as it is showing a smooth trend in case of S block and representative elements, in case of this one, this will show a different kind of a phenomenon. We will discuss this phenomenon in the next class. Okay, so stay tuned or do not forget to see the video again and again, and also stay tuned for the next classes. Thank you. Have a nice day.